Welcome to the third and last in this masterclass series, An Introduction to Mine to Mill. And in this presentation, we're going to be discussing how we can change the feed size of AG and SAG mills through blasting. The principles that we're going to explore are that blasting is the first stage of comminution, and that the ROM distribution influences the SAG mill feed size distribution, and we know that SAG mill feed size distribution influences throughput. And finally, we are able to control blasting in such a manner that we can obtain a desired run-of-mine distribution, and hence through that influence the SAG mill throughput. So how do we know that blasting can change the ROM size distribution? Well, it's intuitive, but the fact is that there have been numerous experiments now where a specific change in blasting has been made and the effect on the ROM distribution has been predictable. And this example here in the graph, which was taken from the paper which is detailed at the bottom, is one very good example of where the ROM distribution has been changed from a standard blast where it was coarser to a more intense blast where it is finer. And there certainly appears to be a fairly systematic change in the shape of the curve. The size distribution of the SAG mill feed from each of those blasts was also monitored at the site, and we can see here that the SAG mill feed for the more intense blast is significantly finer than the standard blast. And the net result of that decrease in SAG mill feed size at the site was an increase in SAG mill throughput of approximately 20%. Now, I want to emphasize it simply isn't a matter of just increasing the blast intensity in the mine to get a finer fragmentation, and then as the comminution technical people on site simply sitting back and waiting for the SAG mill throughput to change. There is the primary crusher in between the ROM and the SAG mill feed, and of course the stockpile, and we've talked about what the stockpile does. But the primary crusher is very important indeed, and the primary crusher has to be used to its maximum to enable the gains from the finer blast to be maximised. And there are two really excellent papers, particularly that of Adrian Dance there back in 2001, he discusses the importance of the primary crusher in mill feed optimisation. And in the other paper by Andrew Scott, myself and David Clark back in 2002, we also discuss about how the primary crusher must be used if you go along the path of finer ROM. And this graph here, I know there's a lot going on in it, tries to illustrate what needs to be done in the case of the primary crusher. And it's been taken from the paper by Scott, Morell and Clark. And what it shows you here on the left hand side is during periods where the gap was 150 millimeters, you can see that the crusher throughput is around about 1700 tons per hour. When the gap is closed to 135 millimeters and nothing else is done with fragmentation, you can see the throughput drops to around about 1600 tons per hour. As soon as the mine to mill blast, however, is done and a finer fragmentation is obtained, then the primary crusher throughput goes back up to almost 2,000 tonnes an hour because it is a finer feed to the primary crusher. And what we're doing here is enabling the primary crusher to produce a finer feed by virtue of the fact that it can close its gap, yet at the same time enable the existing throughput to be maintained, or in fact in this case to be exceeded. And in fact this particular case we got two benefits: one from the overall change in fineness of the ROM, plus some additional finer feed to the SAG mill by virtue of the fact we were able to close the gap down to 135 millimeters and still maintain the high throughputs that were required for the circuit. So we're going to discuss a number of ways that you can blast finer. The first and probably the most popular way of doing that is simply to use more explosive. One can also choose a different explosive with different properties, and one can use the same explosive but in a more effective way by changing the confinement of the blast. And we're specifically going to look at stemming and free face versus choke blasting. Now I want to emphasize again that this is very much an introduction to blasting, so we'll be covering these aspects in a fairly simple manner. They are discussed at more length at the paper that I've detailed at the bottom of the page there, a paper by Andrew Scott, Sharma Kanchi-Bottom and myself that was presented way back in 1999 at the Expo at Kalgoorlie. And I strongly recommend you getting hold of that paper if you're interested in learning a little bit more about the details rather than, in this case, the very simple way I'm going to try and explain how each of these techniques can be used to blast finer. So let's initially look at more explosive, and let's first of all discuss how the amount of explosive is usually measured and represented in drill and blast. And that typically is done using the powder factor term, and that is either represented in terms of kilograms of explosive per ton of in situ rock, or kilograms of explosive per cubic meter of in situ rock. Typically the standard range, so that is not when one's looking to do a mine to mill type operation, then you're looking at a range of very, very roughly 0.5 to 1 kilograms per cubic meter. That depends on a lot of things, not least being the rock strength, and it is a very, very, very rough guide only. Intense blasting, what has been known now as mine to mill blasting, you can easily double those, so going up to between 1 and 2 kilograms per cubic meter. And just to give you some idea of how much energy, that's raw energy in that blast there is, and if we convert that raw energy into the units of kilowatt hours per ton, then if we look at a 0.75 kilograms per cubic meter, which arguably is the average standard blast, then that's putting into the rock, if one presumes that all the energy, so chemical energy, goes into breaking of the rock, you're looking to put into comminution something like between 0.2 to 0.25 kilowatt hours per ton. So we've decided we want to use more explosive. We want to increase the powder factor. How do we go about doing it? Well, let's look at this and assume that this is our initial drill pattern. In this case, we've decided to keep the burden and spacing the same, but to drill bigger holes. Now, of course, if you drilled bigger holes, there is a much larger volume of charge that is put into the blast, and therefore there is more kilograms of explosives put in to that volume. An alternative to the previous strategy is to keep the drill holes the same, but simply drill more holes. And what that means is closing up the burden and the spacing, so reducing those sizes. And in this particular case, we've doubled the number of holes that we're drilling. And in that way, we've increased the powder factor. Now that sounds very simple, as the previous one does as well. One simply says drill bigger holes or drill more holes. From a mining perspective, that comes at a cost over and above the cost of the powder factor. And as a minerals processor, you need to be aware of that. In this particular example here, where one is drilling more holes, that needs more equipment. It needs more drilling rigs. It's going to take longer otherwise. And if you don't have that capacity to drill those number of holes, you've got to find it, and that costs money. So as I've said before, there's no such thing as a free lunch, and there certainly isn't a free lunch here either. So what about changing the explosive type? And if you look at the explosive suppliers at their websites, they have a whole range of different explosives with different properties. The majority of them are based in some way or another on ANFO, and ANFO stands for ammonium nitrate and fuel oil. And that ammonium nitrate fuel oil mix can be used in a number of different ways. It can be used, for example, with the solid form of ammonium nitrate. Now that ammonium nitrate has been processed to provide what are called prills, but it's a solid. And that solid form of ammonium nitrate is mixed with fuel oil that's absorbed into it. Alternatively, you can manufacture a supersaturated aqueous solution of ammonium nitrate and fuel oil, and that's called an emulsion. Or you can have mixtures of the two. Now, I'm not going to talk any more about explosives, or certainly not much more, because it's beyond the scope of this introduction. But bear in mind, ANFO is more or less the basis of all our bulk explosives. And depending on our choice of whether it's an emulsion or we're using it in solid form or mixtures, we can get different densities, and with different densities we can get different weight strength of explosive. And higher densities, for example, typically give us more explosive energy. Now, the other thing that some different explosives can give us is a different, what's called VOD, which stands for velocity of detonation. And that is the rate at which that detonation wave propagates through an explosion within that blast hole. Now, the explosive has to provide both what's called shock and heave energy. The shock part provides the breakage which is necessary for fragmentation, and the heave provides movement of that broken rock, and that movement is necessary to allow that broken rock to be dug and loaded into trucks. If it's not moved, and during that movement it swells and allows itself to be more easily penetrated by a ground engagement tool and therefore dug up. So if you follow that logic, if you have a higher VOD, you will get more of the energy going into fragmentation. But you need to remember, you also will have less energy going into heave, and that could have implications with respect to the ease or lack of ease with which that broken rock can be subsequently dug. So there is always a compromise having to be made there. So now let's go on to look at how you can improve the efficiency of the blast, at least with respect to fragmentation, by changing, in this case improving, the confinement. And we're going to look first of all at the confinement in the stemming zone. Now, without appropriate confinement in the stemming zone, certain proportion of the explosive energy can vent, it's called stemming ejection, out of the top of the blast hole, and that energy is effectively lost. In some cases, mines will use what's called drill chips, and they are not good stemming material. What one is looking for is a material which interlocks in this stemming zone region and prevents the explosive gases from venting out the top. And crushed stone is a far more appropriate stemming material than drill chips. And there are certain rules of thumb with regard to crushed stone type and crushed stone size with respect to the hole diameter. There are also stemming caps that can also be used that are inserted into the top of the drill holes that also help keep those gases inside the volume of material that we're trying to break, and therefore improving fragmentation. Now we're going to look at an example of a blast where there's been poor stemming confinement, and I want you to look for, when this blast video plays, all those drill holes where there's looks effectively puffs of smoke escaping, to identify the number of holes where confinement was very poor. And of course, as I said before, for every one of those puffs of smoke that one sees is a loss of energy that could have gone into fragmentation. Now, this is the same site where improvements to stemming have been made, and so once again watch for the number of puffs of smoke and you'll see how they have significantly reduced. One thing to bear in mind, this video and the previous one does not have a soundtrack, so don't rush to change the volume on your computer. There is no soundtrack. Now we are going to look at a different aspect of confinement, and in this case it is the type of face confinement that we have, and we're going to compare what's called free face blasting with choke. It's also called paddock blasting. Now, if you remember the last presentation on terminology, this face here is called the free face, and free face blasting specifically relates to benches and blasting that have this geometry. And the next two slides have examples of free face blasting where we can see what such blasting looks like. So, having seen those two videos, you will have noticed the amount of energy that's gone into propelling this material here over onto the floor of the pit. That is the heave energy. Now, contrast this with a choke or paddock blast that, viewed very simplistically, has this geometry where there isn't an obvious free face. And conventional wisdom has it that without that free face, the heave energy that would normally go into propelling that material onto the floor is converted into more breakage. Now, unfortunately, I don't have any experimental data to prove that, and so it remains conventional wisdom. Now, you might remember in the previous presentation, we discussed the propagation of the compressive wave when one of these blasts goes off, and the importance of the free face where that compressive wave is reflected back as a tensile wave, and that tensile wave is a much more efficient wave to break rock. So we want a free face. So how do we get that free face when we've got a geometry like that that doesn't obviously have one? Well, the answer is that the drill and blast engineer temporarily creates a free face by controlling the initiation sequence, the firing sequence of each of these holes. Now, in this particular case, we're looking at what's called a center lift, and these yellow numbers down here give us the initiation sequence of those holes. So number 1 is blasted first. That creates effectively here a free face for when blasts 2 are then initiated, and 3 and 4 and so on. A variation on the center lift theme is this geometry, where the first hole that is initiated is on the far right, and subsequent holes are progressed in this direction, 2, 3, 4 and 5 and so on. But the effect is the same in that we are creating a temporary free face by the evacuation of this drill hole through the sequential initiation in this direction. Let's look at a video of a center lift choke blast, and when you watch the video you'll see a series of flashes. This is a freeze frame of the first couple of rows, and you can see that they are right in the center of that paddock, and as the video progresses you will see those bright lines, which are the holes being initiated and set off. You will see those lines radiating outwards sequentially. Now we're going to have a look at the variation that I discussed before of the center lift, where the first hole is initiated on the far right, and you'll watch and see the blast progress from right the way across to the left. I have to say this is one of my favourite blast videos. So hopefully now you've got some indication of what can be done to change drill and blast to influence the run of mine and therefore the SAG mill feed size distribution. And to conclude this presentation, I'd like to have a look at a case history. It's a published case history by Sharma Kanchi-Bottler and his colleagues, and the paper is at the bottom of this screen. It's at SAG 2015. And the case history relates to Paddington Gold, which is a mine in Western Australia. It has a conventional SABCA circuit, and the challenge given to Sharma and his team by the mine was that the ore in future was expected to get harder, and the challenge was, can blasting be changed such that throughput could be maintained despite that harder ore? So the first thing they did was a baseline audit of drill and blast and the SAG mill, and part of that audit was to measure what the ROM was, what the crusher product was, and what the SAG mill feed size was. So that established existing operational methodologies and distributions. Using that baseline data, they calibrated their blast models, their SAG mill models and ball mill models, and then embarked on a series of simulations to look for a blast design, what we've called here an intense blast design, that will get them the increase in throughput that they were looking for. And if you see in this table, you can see what the baseline drill and blast design was and the explosive, and you can see next to it the intense blast as to what they proposed to go to. Now you can see here one of the biggest changes is that they went from a baseline of 115 millimeters hole diameter to 165. And that is the principal way they looked at increasing the powder factor. And you can see here they increased the powder factor from 0.72 up to 1.46. They also chose an explosive with a higher VOD. And if you remember what I said, higher VOD gives you more shock energy. They also increased the bench height. Now, I've not discussed bench height. It's outside of the scope of these presentations. Needless to say, bench height and hole diameter are roughly related, and there are a number of rules of thumb which indicate that if you go to a bigger diameter, typically you will need to have a bigger bench height. But let's just focus on the hole diameter in this particular case as being the principal way in which they managed to increase the powder factor. And you can see here the burden and spacing, it changed slightly, but it's not too far. The intense blast is not too far from the baseline. So they implemented the intense blast and then re-audited both the ROM and the SAG mill feed. And you can see here in the graph, we've gone from the baseline ROM to the intense blast ROM, and you can see the shift to a finer size distribution, which in turn was propagated through to the SAG mill, and you can see the SAG mill feed reduced in size as well. So what happened to the Comminution circuit? Well, from the baseline 307 tonnes per hour during the intense blast treatment of that material, throughput went up to 416 tonnes per hour. That's an increase of a staggering 35%. And the specific energy, the amount of energy used, dropped by no less than 27%. At face value, a huge improvement. But unfortunately, the intense blast was done some time after the baseline, and during that period, the ore became significantly softer. And you can see here the MIA and MIB, these are the, call them the Morel measures of the SAG mill and ball mill hardness respectively, the intense blast values were 18.5 and 13.3 as compared to, during the baseline blasts, the much higher values of 23.5 and 18.1. On top of that, when the intense blast material was being treated, the final grind was much coarser, P80 of 141 versus 103 microns, and on top of that, the circuit was operated in a somewhat different way during the intense blast. There was a higher ball load in the SAG mill and a finer pebble crusher product, both of which would normally give higher throughputs on their own. Now, the authors were well aware of this and they discuss it at length in their paper, and they make some estimates of allowances for the softer ore and also the coarser grind. And when you make those allowances so that you can look at just what did the finer feed effectively give us in terms of a throughput increase, it looks like it gave something like a 7% increase in throughput, which is almost exactly in line with what we would expect from that change in SAG mill feed. If you go back to the earlier presentation that I gave you, that rule of thumb that said that the specific energy will change approximately half percentage-wise what the F80 change will be, then this data point sits bang on line with that rule of thumb. And if you take into account there was a coarser grind and you make allowances for that, there was effectively no change in the total kilowatt hours per tonne. Or put another way, the energy utilisation efficiency in both cases was approximately the same. So, what can we conclude? There is no doubt that when implemented correctly, more intense blasting can definitely reduce SAG mill feed size, and we know that reducing SAG mill feed size increases SAG mill throughput. However, just as with secondary crushing, if the ball mill circuit capacity is limited, then a coarser final grind will result. And within our ability to measure such things, certainly the data that I have suggests that there really isn't any overall change in the energy utilisation efficiency by blasting finer, despite the fact that there are one or two papers that certainly have claimed that this is the case. My advice to you is to look at finer blasting, more intense blasting, in a similar manner that one would look at secondary crushing. And although there might be hidden in the data some changes in energy efficiency, I certainly don't believe there are sufficient magnitudes to warrant any firm conclusions about that. That concludes the third and last in the three-part series, An Introduction to Mine to Mill. If you've not watched the first in this series of three, go to our website at www.smctesting.com/videos to access them, or a range of other masterclass videos concentrating on a variety of comminution topics.